Okay, the next thing I wanted to talk about is something called locality. And locality is actually kind of obvious until I point it out, and then it becomes a bit more interesting. So the idea with locality, this is our tutorial for Monday, is we have at any given point in our domain, we have, for example, oops, temperature. We have temperature at this point, we have temperature at this point, we have temperature at this point, so on and so forth. Now, say we have some quantity of interest, for example, diffusion coefficient. Okay, D is a function of T, and that's equal to, oops, A E negative E over RT. Okay, and now the question is, what T are we going to put in there? If we're evaluating, so sorry, let me back up for a second. If we want to know what the diffusion coefficient is at this point, what temperature are we going to put in? And the answer is pretty obvious, right? It's this temperature. It's the temperature which is local to that point in space, which then goes into that expression. This is the concept of locality, in that a quantity of interest is using variables which are spatially at the same point in the space. The problem is, what if we want quantities which are non-local, which depend on, for example, an average quantity of temperature over our entire domain? So if I asked you for the average temperature, that average doesn't belong to any point in space on that model. It is called a global variable, not to be confused with this global definition. I didn't name them, but that's called the global one. The way that we're going to be able to access this is through something called non-local couplings. So you go over to your definitions, you right click, and there's the option non-local couplings. And we're going to focus on the first four here. They're actually very self-explanatory. There's integration. Want to integrate over a quantity. This is great to see if you have mass conservation, for example, when you're doing diffusion or advection, anything like that. You can make sure that everything is in the volume still integrated to be the same. Average, maximum, minimum, right? Maximum and minimum are going to be great if you want to do something like make sure that the temperature reaches 70 degrees in one place or maximum 100 degrees in another place. All these good quantities of interest, hint, hint, for the design project. Okay. Now, the next thing to note, though, is when you define one of these integration things, you can choose what your geometric level is, they call that. And what that means is, are you considering the integral over this entire line? Oops, I don't have my pen enabled. Are you considering the integral over the entire line? Or this is 1D, so it's a little bit limited. You're going to have to use your imagination. Are you considering integrating over the boundaries here and here, for example? Okay, so that's what that does, right? If we go to boundary, that will instead select the boundary. So domain, oops, selects the whole one, or we can go for our boundaries and then we can choose individual ones. And what that means is that we're integrating that quantity over that geometric level, but we're elevating the result to the global scope, to the scope at which the integral of a quantity over the entire space exists. That's the place where, like, for example, the optimization algorithms work. Because the optimization algorithm will want to work on some kind of figure of merit for the problem as a whole, not just the variable at a particular point. Now, when we go to, I'm going to delete this for clarity. When we go to do this, the way that we're going to define this is basically like a function. Okay, so you right click, you evaluate the integration, and you're going to set up that this is a boundary integral. You're going to choose which boundary it is. It's over here, right? This is part of the tutorial. But that's it. You are never actually putting in the quantity that you want to integrate. Okay, it's basically it's the same idea as when you define a function under here. You've defined your function, but you haven't yet fixed the argument that you are applying that function to. How do you do that? You go into something like variables. Oh, I'm sorry. Here you can see the operator name in top one. You could do something like in here, variables, call this non-local coupling function at CB. Okay, so this is integration at a single point. Integration at a point is a sum. 1 point, it's just the value. And what you're looking for is CB. And the reason they do this is that maybe you also want other quantities, like for example, the temperature at the output stream. You could do it exactly the same. Or you could say CA at out. You would write it the same in top 1, CA. Any of your variables can be defined the same way, and you'll note that the units are populating, so you know that it's right. Okay. This is a very powerful feature. You right-click on here and go to the non-local couplings. I'll get into what the extrusion or projection operators are when we deal with that, because they're a little bit more complicated.